Okay, students, welcome back. We are now entering the homework portion of this course. Today's homework lesson, of course, is homework 9 and chapter 9. And we have homework number 9, chapter 9. The questions we're going to be doing are 48, 55, 57, 59, 60.
Anyone have the page number?
If we call up that PDF, I attached the page numbers, so it's 268. You can actually see the pages right there if you click on the two handouts that I gave you. Okay. Do you guys have that in front of you? Because I could use some help with the reading and such, okay? All right. Don't forget to put your names in homework number 9. And let's begin with chapter 9, number 48. What's the title of this problem? Kayla, are you queued up? Who else is hiding there in the shadows? I want to see. Oh, there's a few of you who are hiding there. Anna and Matthew and Marcos and Peyton and Zach. They're all hiding on me. Okay. Sorry, Kayla. Did you have you want to take that out for us?
Yeah, it's called Miniature Mars.
Okay.
It says, suppose Mars had turned out to be significantly smaller than its current size, say the size of our moon. How would this have affected the number of geological features due to each of the 4 major geological processes? Do you think Mars would be a better or worse candidate for harboring extraterrestrial life? Summarize your answers in 2 or 3 paragraphs.
Okay. Why don't we walk through this together? Let's say Mars had not been the Mars today is what, 3,400 kilometers in radius? Suppose it had been shrunk to about half. The moon is about 1,700 kilometers in radius. Let's review our 4 geological processes. We have impact cratering, volcanism, tectonics, and erosion. We have to address all 4 to get a complete answer. What do you think would happen to, let's leave impact cratering to the side for a second. Well, okay. Well, I don't know. You guys talk to me. What do you think? Which of the 4 geological processes would be affected? If Mars was smaller, would there be any difference to the number of volcanoes you see on its surface? Basically, the question's asking, would Mars still look like this? Oh, I should just, you know what? What happens to what property of a planet is going to be affected by making it smaller? That's what I want.
Would it be plate tectonics?
Okay, well, does Mars have any plate tectonics today? Does it show any evidence of plate tectonics?
It shows evidence that it used to
Maybe,
have plate tectonics.
Yeah, maybe a little bit. And what was the evidence? Oh, shoot. Guys, I can't seem to manage my stupid, no, wait, I don't want that one. I want the PDF. Where are you? There we go. Okay, so where do you see plate tectonics, Jace? Here's the surface of Mars.
In the 3 volcanoes in a row.
Yeah, we saw those 3 volcanoes in a row, which said it must have been some kind of early type of tectonics. I guess if we look in close around here, we can also see some tectonic features like the Noctis labyrinthus. These channels were probably partially carved out by CO2, but this crack started, these look like hard, jagged cracks that formed when the lithosphere got stressed out. Remember, if we looked up close around the Valles Marineris, oops, we could see more examples of tectonic fractures. You can really see them in that nice high-res photo that I showed you guys the other day. You can see all these stress fractures all along the Valles Marineris. Geez, I don't know why I'm having, everything's fighting me today. Life is fighting me today. Okay, well, why would we have less plate tectonics? So Mars shows small amounts of a tectonic history. Today, Mars does not have active plate tectonics, but at some point it kind of had a little bit of plate tectonics. Why would being smaller affect its plate tectonics, Jace?
Because its innards would be cooler, right?
Yeah, that's what the real crux of this question is all about. Remember from one of our previous slides that the interior heat of a planet is proportional to its size. So the big planets have thin lithospheres, but the small planets have very thick lithospheres. And the moon's lithosphere is so damn thick that it goes all the way down to its core. So obviously that would prevent fracturing and breaking apart the planet into lithospheric plates. What else? How about volcanism? Would we still see those big volcanoes at the surface of Mars?
If there wasn't any kind of mantle, then no.
Yeah. If the planet had cooled off faster, you'd lose the volcanoes. What about erosion? We do see signs of erosion on Mars after all. I mean, look at this stuff. Would you see any of that stuff if Mars had been smaller? Put your thinking caps on, students.
I don't see why not.
You don't see why not. Well, what forms do erosion take? What type of erosion is this?
Well, it wouldn't have an atmosphere, so there wouldn't be any wind erosion.
What about water? Can you have water without an atmosphere?
No.
So you want to revise your answer then, right? You wouldn't have any of this
Right.
shit. You can't have water without an atmosphere. You can't have wind erosion. See all these craters, how they look chipped down? See how these pateras are kind of worn down from wind? These craters, those sand dunes that you see, these craters that look kind of chewed up over time, beaten down by wind erosion. Look at this crater here, or this crater here, or these ancient craters that have all been chipped away by wind erosion. Like Schiaparelli looks like it's had some wind erosion or some water erosion. You couldn't have any of that stuff. What about impact craters? Would I see more or less of them?
Probably more.
Yeah. Paradoxically, a smaller planet will show more craters. Why?
Because of no erosion and volcanism.
There's no volcanism to pave it over, so you can't have this smooth stuff. There's no erosion to wear it down. You won't have that stuff. No tectonics. Basically, you'd have the freaking moon. A smaller Mars would look like the moon because it would just be beat to shit by craters and there wouldn't be any other interesting geology at all, right? All right, let's put this into a paragraph. Oh, would Mars be a better or worse candidate for life?
Worse.
Yeah, no atmosphere, no volcanism, no tectonics, no nothing. You're just a cratered rock in space. No one likes that. Okay, let's write the following paragraph together. If Mars had been smaller, say the size of our moon, it would look drastically different than it does today. A smaller Mars would cool faster and the loss of, let's say, internal heat would result in a thicker lithosphere incapable of forming cracks or vents. This means no shield. Shield is IE, I think. This means no more shield volcanoes like Olympus Mons. No volcanism at all unless you had volcanic maria like the moon. Mars would have lost its tectonic features like the valles marineris. I'm going to keep writing here. With no volcanism, no atmosphere, could develop, resulting in a loss of wind and water erosion. This means no more dried up rivers. Okay, it's getting too close to the bottom for me to continue to write it. This means no dried up rivers would exist on Mars. I'm just going to write on Mars. I'm almost done. I got one more bit to add about cratering. Let's just make sure you guys can catch up to me before I go forward. Now, I was probably blocking you for part of that. My body was probably in the way. How are the writers doing? You getting this? Kayla's good. Laura's good. Ernie gave me a thumbs up. How about you, Jillian? How you doing? I'm going to talk to the people that are talking to me, or at least looking at me, or at least letting me look at them. All right, Chrissy, are you still writing? Oh, she's good. Angel? Samantha gave me a thumbs up. Thank you.
Yeah, I'm still writing. I'm starting where it says no atmosphere. That's all I have left.
Okay. Yeah. All right. I'll give you another second or two. Maybe I'll just erase up near the top. I'm going to erase up near the top. So which of our 4 geological processes have I not covered so far? I covered volcanism, I covered tectonics, and I covered erosion. That leaves one thing left to discuss, which is?
Cratering.
Cratering. Okay. And what are we going to say about the cratering?
There would be a lot more cratering.
Yeah. Without active geology, Mars would be overrun by lots of impact craters from the heavy bombardment period. Ooh, we get to work in heavy bombardment. From the heavy bombardment period. In short, which is funny because there's nothing short about this answer, a mini Mars would resemble the moon. A airless, I'm going to put airless in quotes because Mars doesn't actually have air, an airless cratered rock incapable of supporting life. Unless it was some kind of whack alien stuff that could survive in the vacuum of space, like tardigrades. Okay, Angel, since you were dragging up the rear, let me know when you're finished and we'll move on.
Yeah, I'm good. You can erase the stuff at the bottom. I already have all that.
Oh, okay. I'll just give you one more second here because I'm sure there's got to be someone still writing. Okay, I am prepared to move on.
I'm still copying some of the stuff on the top. I'm sorry, I'm
Okay.
a slow writer.
That's okay. That's okay. Matthew, just let me know when you're done, okay? If that was Matthew. Shoot, that took up a lot of time. I've got to move faster. Matthew, how you doing?
Almost done. I'm on the last sentence.
All right. That should have been Anne, but whatever. Okay, Matthew, we good?
Yeah, what is that word on the last sentence say? It says an airless what?
Cratered rock. Sorry. I was writing badly and fastly. Cratered rock incapable of supporting life.
Cratered rock incapable of supporting life. Okay, you can erase that.
Okay.
Thank you.
Yep, my pleasure. Okay, Kayla, hit me with some number 55.
This one's called surface area to volume ratio.
Oh, this one's easy. By the way, the book wants us to compute the surface area to volume ratio. We instead are going to compute the volume to surface area ratio. You guys will remember, or you will have forgotten, that in last class we came up with this concept of volume to surface area ratio, which is proportional to 1/3 the radius of the planet. And this, we decided, was an indication of the amount of internal heat of the planet. Sorry, I just had to mute Matthew there. That's an indication of the amount of internal heat. The book was trying to get us to do the surface area to volume ratio, which is inversely proportional to radius. And they want that to be proportional to your cooling rate. That's a little bit wonkier because we have to have radius in the bottom. Let's do this one instead. Okay, Kayla, read it out for us.
Compare the surface area to volume ratios of A, the Moon and Mars, and B, Earth and Venus. In each case, use your answer to discuss differences in the internal heat of the two worlds.
This is super, super easy, okay? Come on, focus. All right. We're going to write it like this. We're going to have the volume to surface area ratio for Mars. We're going to divide it by the volume to surface area ratio for the Moon. And that means at the top, we have 1/3 the radius of Mars over 1/3 the radius of the Moon. The 1/3s will cancel each other out, and I can simply put in the radii of the two planets. The radius of Mars is 3,400 kilometers. The radius of the Moon is 1,700 kilometers. What does that give us?
Two.
Angel, I thought we were under the covers with you for a second there.
Yeah, my kitchen is pretty cold. I don't know why.
Really?
It's like a breeze somewhere.
Yeah, it's been kind of a cool spring. Where's my warm days? I want to take a bike ride.
2.
2 is what you
Yeah.
got?
Yeah.
And what's the meaning of the 2, Laura?
It is 2 times larger than the Moon.
But
No,
it's not about the largeness.
the mass.
It's not
Volume.
no. You're missing the bigger point, the zoom out point.
The internal heat.
Okay, so walk me through the logic then.
I have no clue, but
No, come on, you're doing it. You're doing it.
so Mars is 2 times the internal heat of the Moon.
Pretty much, yeah. Mars holds 2 times more internal heat than the Moon. Another way to look at it would be the Moon cools off 2 times faster than Mars. Okay, what's our letter B, Kayla? Pushing it forward.
That would be Earth and Venus.
Okay, Earth versus Venus. So the volume to surface area ratio of Earth divided by the volume to surface area ratio of Venus will go as the radius of Earth divided by the radius of Venus. And that's 6,400 kilometers over 6,050 kilometers. And that's approximately equal to what? Big picture, simple concepts.
1.
Yeah, that's approximately equal to 1, meaning that Earth and Venus hold similar amounts of internal heat. And boom, we're done with that problem. That stuff is real easy. Are we cool? Matthew, can I erase?
No, I'm still copying, sorry.
All right. That means it's iced tea time for me. Thanks. Let's just say we're not having our best morning over here in the Britain residence. Some dehydration going around. Okay. Can I erase now, Matthew?
Yeah, you can.
Okay.
Thank you.
Meg's going to prison?
Okay. Kayla? 57.
57. It's called Lunar Footprints.
No, for just like.
It did. Like the delivery truck?
Oh, man.
Class, get ready.
That'd be cool if my chair was in there.
All right, hold on. I gotta mute that. Where is he? Mute. Okay. I want to try to talk to you guys about what this problem is about, because this problem's a bit of a whopper. It's a whoopee-doo, okay? Maybe the biggest whoopee-doo we've had all semester. And I want to show you guys a legendary picture from the Lunar Landing that you might have heard about before. When they got to the surface of the moon, they discovered that the surface of the moon was not hard rock, but the entire surface of the moon was ground up into a fine powdery surface known as the Lunar Regolith. And I've got a couple of pictures from US space history to share with you here. So let's go to 87. Can you guys see the dust getting kicked up underneath the tires on that lunar rover there? Here's another photo. Here you can see all the footprints in this fine powdery soil. Basically, the entire surface of the moon is covered in a 3 to 4 centimeter thick layer of, let's just call it what it is, moon dust, silicate moon dust. And how did that moon dust get there? Because the moon has absolutely no atmosphere, every tiny little pea-grained pebble and bit of sand that strikes the moon is creating a little pit or a crater. And over 5 billion years of being impacted by little grains of sand, the moon's surface has become ground up into a fine powdery dust. Look at all the footprints that the astronauts are leaving in the sand. And here's a close-up picture of Neil Armstrong's boot in the Lunar Regolith. Now, if this was on Earth, Neil Armstrong's boot would be washed away in a day or two by a hailstorm or a rainstorm or something like that. But think about the surface of the moon. It's touching the vacuum of space, right? There's never a gust of wind, never a drop of rain. Neil Armstrong's boot print will stay perfectly preserved in the moon for, well, I don't know. Maybe we should work it out in this problem. Okay, take it away, Kayla. Read the question.
It says, assume that the moon is hit by about 25 million micrometeorite impacts each day. This number comes from observations of meteors in Earth's atmosphere, and that these impacts strike randomly around the moon's surface. Also assume that it takes about 20 such impacts to destroy a footprint. About how long would it take for one of the footprints left by the Apollo astronauts to be erased? And use the moon's surface area to determine the impact rate per square centimeter and estimate the size of the footprint.
Okay. The moon is impacted by 25 million micrometeorite impacts per day, which I am cheekily calling moon imps per day. A footprint will be destroyed if, now the only thing that can destroy Neil Armstrong's footprint is more micrometeorite bombardment. And 20 of those little impacts on the foot, or foot imps, will destroy your footprint. Our picture is of a big disc, and there's kind of a little footprint on it. And we're trying to figure out how many of those impacts that strike the moon are going to be hitting Neil Armstrong's foot. Let's have a thought argument. Class, suppose Neil Armstrong's foot was so damn big that Neil Armstrong's foot covered 1/4 of the moon's surface area. If the foot was so big that it covered 1/4 of the moon, what fraction of the moon impacts would strike the foot each day?
1/4 of them?
Yeah, 1 in 4, right? And that tells us, okay, what if Neil Armstrong's foot was 1/8? Then 1/8 would hit them. What if it was 1/10? The idea or the concept is that the probability of a single impact hitting the foot is going to be the area of the footprint divided by the area of the moon. Basically, it's the ratio of areas. And you know, this holds in darts too. If your bullseye is 1/50th of the surface area of your dartboard, then you have a 1 in 50 chance of randomly striking the bullseye if you throw darts at a dartboard. That's assuming that you have no skill, but enough skill to hit the dartboard, which is kind of funny. In fact, let's imagine that we invented a computer program that played darts with us. And this is called in physics the Monte Carlo method, after the famous gambling resort. Our computer program is going to be throwing darts at a moon-sized dartboard, and it's going to be striking the dartboard with 25 million darts per day. Our first job is to figure out what's the probability that a single dart will end up hitting Neil Armstrong's boot. Okay, the area of a foot, if we imagine a rectangular foot, is its length times its width, right? So here we can use my boot as an example. I was hoping that today I'd get to use my iPhone share effect for some nefarious purpose. A plugin. Why does it keep asking me to install the plugin? Hold on a sec, guys. I'm just grouchy and crotchety today. Let me make sure I'm Wi-Fi connected. Yep. Okay, so, all right. So here's some centimeters. Here's my boot. Okay, roughly how long do we think a boot is? Maybe 30 centimeters, right? And how wide is a boot? Neil Armstrong's boot's probably a little bit wider than that, but oh, maybe 10 centimeters, right? Okay, thanks for playing. So, so the area of our foot is 30 centimeters by 10 centimeters, or 300 centimeters squared. What about the area of the moon? Well, the area of a sphere, the surface area, is 4 pi r squared, which is 4 times pi times 1,700 kilometers. Does anyone out there remember the conversion factor from kilometers to centimeters? Because we should get these in the same units. How do I convert from kilometers to centimeters?
A kilometer is 10 to the 5 centimeters.
Okay, so let's do this. Let's do 4 times pi, 1,700 kilometers times 10 to the 5 centimeters per kilometer squared. That's a fast way to get the surface area of the moon. And you can plug it into your calculator, 1700 EXP5 if you want. What do you get?
.6 times 10 to the 17.
Units?
Centimeters squared.
Yep. Okay. Let's plug that into our probability. The probability is 300 centimeters squared over 3.6 times 10 to the 17 centimeters squared. What's that give us?
.3 times 10 to the negative 16.
What are the units, Kayla?
I don't think there would be units.
No, there aren't units. What does it mean? What's the meaning of 8.3 times 10 to the minus 16, students? What's the meaning of that number? Okay. Take a load off, Fanny. Take a think back to our giant imaginary boot, which is so big that it covers 1/4 of the moon's surface area. If you divide 1 by 4, you get 0.25, no units. What is the meaning of 0.25?
A quarter of the moon? Is that what you're saying? No.
Kind of, but we're talking about a probability here. I'm trying to get you to think about what this number means. And I'm trying to get you to think about the probability. And just think about probabilities in general. If I have a probability of 0.25, what is the meaning of that?
The chances that it would happen. I don't
What
know.
would happen? What's it?
1 in 4.
Right, a 1 in 4 chance that what would happen?
One of the particles will hit the surface.
1 out of every 4 particles will hit the surface. Or another way to interpret that is 25% of the particles will hit the surface, correct? I ask again, what does this mean? 8.3 times 10 to the minus 16.
That's the probability that one of the particles will hit the footprint.
We'll hit this guy over here, right? It's a super small probability. A single micrometeorite can land anywhere on this moon. The chances it's going to hit Neil Armstrong's footprint is not exactly 0, but it's getting pretty fucking close at 10 to the minus 16, right? Now, probabilities don't have any natural units, but that does not mean that we cannot assign them units to be clever and to keep our brains straight. For instance, if the probability had been 1 in 4, we could say it's 1 foot imp for every 4 moon imps. Or we could say it's 25% chance of getting a foot impact over a moon impact. Now, both foot imps and moon imps are dum-dum units. They're not real units. They're not measuring anything. And since they're both impacts, they can kind of cancel each other out. So we haven't violated any rules. But it might be helpful for you guys to think of this as the ratio of foot impacts to moon impacts. Let's go ahead and add that to our number, because units, as you all know, help you think. This is the ratio of foot impacts to moon impacts, or foot imps to moon imps. Okay, what is it that I'm trying to do here, class? What's the problem? Ask me. Because I can't even remember what the damn question was asking anymore. It's so convoluted.
It wants to know how long it would take for one of the footprints left by the Apollo astronauts to be erased.
Okay, maybe we should try to figure out how many how many times the foot gets struck in a day. How many meteorites strike the moon per day?
25 million.
Okay, so what should I do with that? What should I do with this, and what should I do with that? Think dimensional analysis. I give up. It's too hard. I can't figure it out. I need your help, class. My brain is broken. I can't do this without your help. I could sure use some big thoughts right now. Y'all got nothing for me?
Divide them?
Well, what will happen if you divide those? Like, for instance, which are you going to divide by which?
Are we supposed to multiply that number by 25 million?
What would happen if we did that? What will the units be? If we take...
moon impacts.
Careful. Wait, 8.3. Let's look at multiplying first. 10 to the minus 16 foot imps per moon imp. And if we times it by 25 million moon imps per day, what will my final units come out to be, Jillian? Do you see where I'm going with this? Or do you see where you're going with this? Because this was your idea.
Yeah, I think it might have been a bad idea.
Why?
I figure that it might be like a goofy non-unit of like foot impacts per moon impacts per day. But as it's coming out of my mouth, it kind of
you're
sounds
on the right
not
track
as
here,
dumb.
but you're just missing something. You're missing something really obvious. Everything you're doing is saying is correct, but what are the final units be? I don't care about the numbers. I want to know what the units are doing here.
Well, is it not foot impacts per moon impacts per day?
It is not foot impacts per moon impact per day, because you have moon impacts here as well as there.
Okay, so foot impacts per day.
That sounds good. That's what we'll have. And that seems to get me closer to my goal, because I don't really care how many micrometeorites hit the moon per day. I want to know how many times per day the foot's getting hit. All right, multiply them up. What do you get? What do you get?
2 times 10 to the minus 8.
Okay. You get 2 times 10 to the minus 8 foot imps per day. Okay, I need some big thoughts here. What should I do next?
Was the question?
Yeah, what is the question? Kayla, remind us what the question was.
How long would it take for one of the footprints left by the astronauts to be erased?
How long? We're looking for time. How long to erase the footprint? Hey, by the way, Jace, what does 2 times 10 to the minus 8 foot impacts per day mean? What does it mean that I'm getting 10 to the minus 8 foot impacts per day? I'm trying to understand that.
It's still a probability, right?
It's more like a frequency or a rate. It's not a probability anymore because it actually has units of days. Think of it as hits per day, foot hits per day, foot smacks per day, something like that.
So we're not even getting a whole foot impact a day, but we have to get that number up to 20 to see how long it would take.
Yes, Kayla, you are thinking correctly. This is what I want to hear. That's what I want to hear you say. Kayla's got the point. In a single day, Kayla, I'm not even getting one hit, am I? I'm getting 10 to the minus 8 hits, whatever the hell that means. It's not like the micrometeorite only breaks into 10 million more pieces or something. Okay, maybe, Kayla, we have to flip our thinking. And I want to say that in capital letters. Flip our thinking. Maybe it would be interesting to know how many days until we got 1 foot impact. How would I get that? How can I flip this around so that I get a number of days until I get 1 foot impact?
Would you do 1 over 25 times 10 to the 6? Days
That will
per-
give you days per moon impact.
Okay, so you want to do. I don't know.
Wait, I'm sorry. Yeah. You were almost there. You picked the wrong man out of the lineup there.
So 1 over 8.3?
Oh, geez.
No.
What was I trying to get again?
You're trying to get foot per day?
I have foot impact today.
You want days per foot.
Impact.
Yeah.
Days per
So
foot
1
impact.
over 10, 1 over 2 times 10 to the negative 8?
Yes, we take the reciprocal of that number. And what is 1 over 2 times 10 to the minus 8? So now this will be days per foot impact. And what do you get?
50 million?
50 million days in order to get 1 foot strike or 1 foot impact. Now what do I do?
Now you're trying to find out how many of the 20 foot?
Yeah,
Multiply by 20.
Multiply by 20 foot impacts and we'll have our answer. Because if we multiply by 20 foot impacts, that'll give us the number of days to destroy the foot. And what does that turn out to be?
A billion days? I got a billion.
1 billion days. Shit, that's a lot of days. How many years is that? What's our conversion factor?
Almost 3 million years.
Holy smokes. Neil Armstrong's footprints will be etched in the moon for the next 3 million years because there is never a gust of wind to blow those little moon dust pebbles around. Holy schmoly. See all those footprints there? One small step for man, one giant step for mankind. Those footprints, ironically, there's the American flag. The American flag's already probably been bleached by ultraviolet and X-ray radiation, and the flag is probably in tatters and is just a white shred of cloth, if it's anything. Meanwhile, the footprints will survive for the next 3 million years. Maybe they should have stomped the American flag into the ground. That would have lasted longer. Kind of a cool problem. Okay, you guys got all that? Because time's money here. And I'm looking to rent a couch. By which I mean take a big nap. Okay, I'm going to erase. Okay, 59. Hit me.
It's called internal versus external heating.
Okay.
In daylight, Earth's surface absorbs about 400 watts per square meter. Earth's internal radioactivity produces a total of 30 trillion watts that leak out through our planet's entire surface. Calculate the amount of heat from radioactive decay that flows outward through each...
Can I interrupt you?
Yeah.
How many zeros are in a trillion?
12?
Very good. Okay, so continue from 30 trillion watts. Sorry.
30 trillion watts that leak out through our planet's entire surface. Calculate the amount of heat from radioactive decay that flows outward through each square meter of Earth's surface. Your answer should have units of watts per square meter. Compare quantitatively to solar heating and comment on why internal heating drives geological activity.
Okay, so here's our problem. Our problem is that I've got little radioactive isotopes spread all throughout the Earth, and they're producing 30 trillion watts of power in all directions. My goal is to figure out how many watts are flowing through a square meter. And then I want to compare it to sunlight, which is striking from above. This sounds like a job for what classic formula class?
Inverse square law?
Yeah. We want to calculate the brightness due to radioactivity, and the brightness is luminosity over 4 pi r squared. Now the radius of Earth, 6,400 kilometers, can be converted to meters by multiplying by 1,000. That gives me 6.4 million meters. I'm going to accelerate this program a little bit here. So the brightness would be 30 trillion watts divided by 4 times pi times 6.4 million meters squared. You guys punch that up for me. This is geothermal, by the way. This is geothermal energy. What'd you get? I took 1 bite of raviolis. That should have been enough time for you to get the answer.
I got 0.05, but I don't think that's right.
Why not?
I got that answer too.
I don't know.
What did you think was the right answer, Chase?
It just didn't seem, it just seemed like a weird answer. I don't know.
Oh, are some answers weird?
I guess so.
Actually, that is kind of weird. I'll tell you why it's weird. It's supposed to be weird. Because how does that compare to sunlight? If you take the ratio of 400 watts per square meter to 0.05, what do you get?
$8,000?
8,000? And what's the meaning of that 8,000?
8,000 times smaller?
Less than the sun. That kind of begs a real question here, class. And I want to state the question. So here's a cue. If geothermal energy is 8,000 times less than sunlight, how does it drive geology? Like plate tectonics and volcanism. How can geothermal energy be the source of volcanism and plate tectonics when the sun is 8,000 times more powerful? What do you think the answer to that question is? Any thoughts?
Well, the heat's coming from a different direction.
Kind of, Caleb, that's the right answer. What happens to the sunlight when it hits the surface of the earth?
It's absorbed by the ground.
And then, what after the rocks heat up, what do they do?
Cool back down.
How do they cool back down?
They radiate away the heat.
They
Yeah.
re-radiate the heat back into space at infrared wavelengths. But geothermal energy has to flow across the boundary of the lithosphere by what process? What heat transport process?
Convection?
No. Convection only works if you have blobs. Well, it's convective in the asthenosphere, but the lithosphere is frozen and brittle. So it must be what? Oh.
Conduction?
Conduction. That's right. This is about the direction of energy flow. Answer. Sunlight is absorbed by the surface, maybe like the top half a meter, and re-radiated back into space. On the other hand, geothermal thermal energy flows across the lithosphere by conduction, which drives geology. But Jace, in a way you were right. It is pretty freaking weird that all of the energy that's creating volcanoes and earthquakes is 8,000 times weaker than sunlight. This is why sunlight drives your surface temperature, but the amount of geological activity you see on a planet is driven by its size and its internal heat. That's the message of this story. Okay, we got one problem left. I hope it's an easy one. Matthew, friends, can I erase?
Yes.
Okay, I'm erasing. Shout at me if you don't like that. Okay, for our final act, Chapter 9, number 60.
It's called plate tectonics.
Oh yeah, this one's an easy one. I figured we should have an easy one at the end. Okay.
Typical motion of one plate relative to another is 1 centimeter per year. At this rate, how long would it take for two continents 3,000 kilometers apart to collide? What are the global consequences of motion like this?
Okay. This is me trying to draw Africa and South America and failing pretty freaking badly, okay? These two continents are maybe 3,000 kilometers apart, and the velocity of plate tectonics is, what did you say again?
It's wait, sorry, I lost it. 1 centimeter per year.
Okay, what should I do? Oh, what do I want to find again?
How long would it take for two continents 3,000 kilometers apart to collide? And what are the global consequences of motion like this?
So I have a distance, and I have a velocity or a rate, and I want to solve for time. How do I do that?
Should convert kilometers to centimeters first, no?
I think that's a great idea. What's the conversion factor again?
10 to the 5 centimeters per kilometer?
Excellent. So how many zeros do I have then?
8.
Now what do I do? How do I solve for time? Time? You know, I'm pretty sure on those damn SAT tests, they ask you to do like a distance equals rate times time problem. You know, train A leaves the station at 50 miles per hour. Train B leaves. So.
Wouldn't it just be 3 times 10 to the 8 years?
I guess so, yeah. Let's do the math though. Time is distance divided by rate. So 3 times 10 to the 8 centimeters over 1 centimeter per year. And yeah, Jace, you're right. Or 300 million years. That's part of our answer. What do they ask us to do for the follow-up? What is the meaning of 300 million years then? What's the significance of that number?
That's how long it'll take before they collide.
Yeah, but if you zoom out and think on bigger scales, what does it mean for planetary geology?
That's how long it took for them to separate.
Yeah, but now take it to the next logical thought step. That's how long that's how long it takes to go from Pangea to today. But on a planetary geology kind of scale, like if you're thinking about planets, let me just tell you the freaking answer. This defines a geological time scale over which the surface of Earth is refreshed due to plate tectonics. Basically, there are no lumps of rock on Earth that are much older than 300 million years. Because every 300 million years, you bash all your bumper cars together and you screw the thing up and you repave your driveway. By the way, a curious note, some of the oldest continental crust on Earth is the continental crust of New England, over which you are standing right now. That's good. That means we're not subject to earthquakes like those irascible Californians. All that sunshine, as you know, is bad for the brain, rots your mind. Okay. You've wasted another afternoon learning about planetary science. Did I? Oh my God, please tell me I recorded this. Yes, I did record this. Okay. So, you guys know what you need to do. Please make sure you're keeping up with the submissions. All of you that I'm seeing here are always good boys and girls, and you guys turn in your work. So I ain't worried about you. But there are some people that I literally have not seen or heard from once. And they better have some bad coronavirus shit going on, because I'm worried that they have not submitted any work and the end of the semester is coming. I think, is next week our last week, or do we have 2 more weeks? 2?
Well, we're not doing a final, right?
Yeah.
I think it would be 2 more weeks if we had a final.
So then it's 1 more week of lecture, right?
I think.
Yeah, because otherwise you know what? Why don't we get to the bottom of that right now? Oops, sorry. I can't make up my mind what I'm doing here. Let's go to Ccri Calendar. Boy, fall 2020 really took a weird turn. So final exams, oh shucks, I lost it. Basically, our final exams would start like Monday or Tuesday. So Monday, May 4th. And that means we have one more week of lecture. So we'll have class on Monday and class on Wednesday. And then we're all still planning, I guess, to double our exam score so we don't have to take a final, correct? Well, cool beans. We're getting to the end pretty fast. I probably ought to send out an email to everyone saying, hey, if you've been slacking, this is the time. This is the time to try to watch 50 million YouTube videos and do all your work, which is not going to be easy. Okay. Great seeing you guys as always. Live long and prosper. Like, comment, subscribe, and don't forget to turn in your homeworks. Okay? Okay. Bye-bye.